due to Frenkel defect, no change in density, but dielectric constant increases, because here increasing the cations into the interstitial positions, that's where the dielectric constant will be increases. So number of Frenkel defects we can measure by the equations. So here number of Frenkel defects we can measure by using the formula. Number of Frenkel defects is equals to square root of n into n prime into e to the power of wf by 2 kt. So see, n is equals to number of sites per centimeter cube that could be left vacant, left vacant, and n prime is the number of alternative interstitial positions, alternative interstitial positions. So Wf, you know that work necessary to form the Frenkel defect. K is the Boltzmann constant. T is the absolute temperature. So if you see this diagram for the Frenkel defects, there are metals and there are cations plus charge, and anions minus sign, plus cation. Here another anion metal cation is there, so anion, and here anion is there, so cation. Next if you see here, it is anion, so X minus. But here if you take the any metal cation will go into that interstitial positions, so here it is metal plus, so it is accommodate somewhere here. So this is due to it occupying the vacancy, so it is replacing the position of the metal here to here, from here to here. So here there is no change in the density, so here there is no change in the density, but dielectric constant may increase due to the presence of distance between the two anions and cations. So this is about the stoichiometric defect. Stoichiometric defects are two types of defects. One is Schottky defects and one is the Frenkel defects. Next thing is defects in non-stoichiometric defects in non-stoichiometric compound. Non-stoichiometric compounds. So defects in non-stoichiometric compounds. So the compounds in which what is first of all the non-stoichiometric compounds? The compounds in which the ratio between number of cations to the number of the anions is not equal to to ratio indicated by chemical formula, to ratio indicated by the chemical formula, so here the chemical formula ratio is not equals to the ratio between the cation and anions, then we can say it as it is a non-stoichiometric defect. So formula are called non-stoichiometric non-stoichiometric defect. So defects, non-stoichiometric defects, further classified into two types. So these are two types. One is metal excess defect. Metal excess defect. If you see the metal excess defect and metal deficient defect. So first one is a metal excess defect. Simple it is. If there are cations and anions, if there are cations plus m plus and x minus, see here m plus and x minus, and if you take the x minus and here is a m plus and it is x minus, and here it is m plus. Next, if you think, so here m plus x minus and m plus x minus, here excess of electrons were present here, so these are called F centers. So here these are called F centers. Then these are the metal excess defects. So here if you see, electrons are there. How many metals are there here? 1 2 3 4 5 6 metals are there. How many anions are there? 1 2 3 4 5 anions. Only 5 x minuses and 6 m plus. So this we call it as metal excess defects. Next, if you see metal excess defect, these centers we call it as F centers with a color center due to the presence of unpaired electrons. Next, if you see here if you see anion vacancy is occupied by the electron. The electrons are called F centers. Greater the F centers, greater is the intensity of the color. Greater the intensity of colors, because presence of this F center free electron, when you apply some light or electric field, it can excite into the higher lowest unoccupied molecular orbitals, and immediately it jumps into the same highest occupied molecular orbital, so it emits some radiation. That is, number of F centers are higher, then we can say it as more colored, and intensity of the color will be increases. Next thing is metal deficient defects. So we will see the metal deficient defects. Thank you.